Hi there, welcome back to the channel, and in today's video I will be introducing complex numbers. So I'll be trying to cover as much as I can about complex numbers and all the different ways you can view complex numbers so that you can better understand it. I'll also be discussing polar and rectangular form as they are the two forms that complex numbers can be presented in. And I'll also be showing a few examples of why we use complex numbers from the standpoint of electrical engineering, and I will also be providing some problems in this video for you to solve. So complex numbers are comprised of a real number and an imaginary number. So let's start by discussing those. In everyday life, you will be using real numbers. For example, if you needed to go to the shop and buy 4 hamsters, that's an example of real numbers. And imaginary numbers are, however, not so easy to interpret as a real number. Imaginary numbers, typically represented as I or j in a formula, are equal to the square root of -1. Typically, if you were to enter this on a calculator that's not in complex mode, it wouldn't be able to calculate it because it's normally not possible. However, if you did have it on complex mode, you would get I or j. So what it essentially is a different dimension of number that we can use to our advantage. And it should also be said that we use j as to represent the imaginary number in electrical engineering calculations, because you could easily confuse I, the imaginary number, with I, the current. So following on from that, let's consider a unit circle to help us visualize real and imaginary numbers. So what we essentially have here is real numbers on the x-axis and the imaginary number on the y-axis. And let's start by having a closer look at j, the imaginary number. We know that is equal to square root -1, but in terms of the unit circle, in polar form, j would be equal to ej pi over 2. Pi over 2 is 90 degrees, and that's because we have to move from 1 to j by 90 degrees. What would happen if we were to square this term? What would happen if we squared the imaginary number? You could see this in two ways. If we take the square root away, we're left with -1, since we squared j. And in terms of the unit circle, once again, we have to move 180 degrees from 1 to -1. So it's equal to ej pi. And if we were to cube this term, we would get -j from the unit circle, and that would, in polar form, would be equal to ej 3 pi over 2. And to conclude this, if we were to raise j to the 4th power, we would be left with 1. And in terms of the unit circle, that's equal to ej 0, because we don't have to move to get to 1, basically. And it should be known that any number to the power of 0 is equal to 1. So a general trend here is that every time we raise j to a new power, like 2, 3, and 4, we move it by 90 degrees each time. And you might be wondering, well, what's polar form? I'll be explaining this shortly. So before I fully discuss polar form, let's first cover rectangular form, as that's another way complex numbers can be shown to you. Let's say we have some variable, x equal to a real number, and jb, an imaginary number. This is rectangular form of a complex number, and you should know that you you can take a conjugate of rectangular form, and what essentially that does is just changes the sign from minus to plus, plus to minus, and if you were to take a double conjugate, the conjugates would basically cancel out and you wouldn't really have to worry about it. And it should be said that rectangular form is ideal for adding and subtracting. Now, even though it's ideal, you can still simplify a fraction of complex number in rectangular form, such as this. Let's use this as an example. You could actually simplify this in rectangular form, such as this. You would use the conjugate of the denominator, like this, multiply the top and bottom by the original bottom conjugate, and this would simplify into 10 minus j21t plus 10t squared over 4 plus 25t squared. And now let's cover polar form. Polar form is represented in this way. Or I should use x in this case. This x with the two lines on this left and right means the magnitude of the complex number, and theta represents the angle of the complex number. And it can also be represented in this way. They both mean the same thing, but it's just a different way of displaying it. Now, what do I mean by magnitude and angle? Let's consider a real and imaginary plot, such as this. Let's say we have some imaginary number here and some real number there. They would intersect here, and the line from origin that meets this intersection, that is the magnitude. And the angle of this line is theta. So we can use polar form to observe the magnitude and the angle of a rectangular form complex number. So it can be said that polar form is ideal for multiplying and dividing. And you need to know how to convert between the two, so I'll show you now. To convert from rectangular to polar, let's use the left example, x equals a plus jb rectangular. To get x with the two lines next to it, the magnitude, you take the Pythagoras of the real and imaginary number, such as this. And to get theta, that would be equal to the inverse tangent of the imaginary number over the real number. And to convert from polar to rectangular form, I'll draw it on the rectangular side here. Let's say we have x magnitude e j theta is equal to x magnitude cosine theta plus j x sine theta. So that is the real part, and that is the imaginary part. That's how you convert between the two. And to use polar form for multiplying and dividing, I'll show you that right now. So let's say we have x1 and theta1 over x2 theta2. Running out of space here. So that would be equal to x1 over x2 and theta1 minus theta2. So what you essentially do here is divide the magnitudes and subtract the angles in this way. And to multiply the two, it would be like this. You would multiply the two magnitudes, and this time you add the two angles together. So that now covers rectangular and polar form. So now you know how to use rectangular and polar form. Let's have a look at some examples as to why we use complex numbers. I can show you some examples from the standpoint of electrical engineering. So let's first consider an AC voltage formula. Voltage as a function of time. What function of time means is that this formula for the voltage will depend on time, basically. It's time dependent. So that will be equal to Vp, the peak voltage, multiplied by some function sine or cosine because they oscillate uniformly and therefore alternate. So let's use sine in this case. Sine of omega t, and omega t can have a phase shift, and that's represented by phi. And that phase shift can be in degrees or radians, just so you know. So by using complex numbers, we can represent this in phasor form. So here we have a voltage phasor equal to the peak voltage with the phase angle of the phase shift. So by converting this into a phasor using complex numbers, we eliminate the time dependency of this formula, and we also conveniently observe the phase shift. So that's a polar form example. Let's consider a rectangular form example. So we also, in electrical engineering, deal with impedances. And impedance is resistance and reactance. So we don't really deal with resistance all the time, because sometimes we can have a reactance. And it does a similar thing to resistance, but in a different dimension, so to speak. So we use imaginary to represent reactance, and we can combine the two together to represent a total impedance. That's a rectangular form example. So let's now consider an inductor. Which has a voltage drop across it, represented as VL. VL is equal to the inductance of the inductor multiplied by the derivative of the current with respect to time. Normally, that would be quite a painful equation to solve, to find the voltage drop across the inductor. But by converting this into a phasor, we can eliminate that derivative term. So here we have V phasor L over I phasor is equal to J omega L. If you're wondering how that happened, I used this property. The derivative of something, let's use zt as an example here, that can be converted to j omega z phasor. So I did that to the current basically and divided both sides by the phasor current to obtain an equivalent formula for the impedance of the inductor. And that covers a few examples there as to why it's important. So let's now put theory into practice and solve some problems. Okay, so what I want you to do for this first set of problems is to convert these complex rectangular numbers. So let's start with part A and start by finding the magnitude. So that's the square root of 3 squared plus 4 squared is equal to 5, and the angle is equal to inverse tangent 4 over 3, and that's equal to 53.13 degrees. So our final answer here is a magnitude of 5 with an angle of 53.13 degrees. And let's start with part B now and find the magnitude for that. So the magnitude here is 3 squared plus 1 squared is equal to square root 10, and the angle is inverse tangent of 1/3 essentially here, and that's equal to 18.44 degrees. So now we have the components of polar form for that rectangular form expression there, but it's in the denominator, so we have to divide 1 by this polar form. So here we have 1 over square root 10 equal to square root 10 over 10. That's our magnitude, and our angle here is just going to be 0 minus 18.44, so that's minus 18.44 degrees for our angle, and that's your solution there for part B. Now for part C, let's find the magnitude for that. Minus 2 squared plus 5 squared will give us an answer of square root 21, and our angle here is inverse tangent of imaginary over real. It will give us an angle of minus 68.19 degrees. But let's check the quadrants here in the top left of a real and imaginary plot. The convention for angle is that a positive angle travels anti-clockwise and a negative angle will travel clockwise. So we just calculated the angle and it's minus 68.19 degrees. That's going to be in quadrant 4. But our answer should be in quadrant 2, shouldn't it? Because we have a negative real and a positive imaginary, so it should lie here, your answer. So to account for this error, you have to add 180 degrees. So by adding 180 degrees, we get a final answer of 111.8 degrees for our argument angle. So our final answer for C is actually square root 21 as the magnitude with an angle of 111.8 degrees. So what I hope you learned here is that you should always check the quadrant that your answer should lie in, because if you didn't account for that and check, you would have gotten the wrong answer for C. And for those of you who don't know, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So moving on now, let's move on to the next set of problems for you to solve. For this next set of problems, what I want you to do is to convert these polar form expressions into their rectangular form equivalents. Pause the video if you need to work on the solution. So let's start working on a solution for part A. We can write it out this way to obtain an expression for the real and imaginary part in rectangular form from the polar form. And this is equal to 3 times square root 3 over 2 for the real part, and for the imaginary part that is equal to 1.5. So that's a solution for part A. Now for part B, we start by rewriting j in its polar form equivalent. And we raise this to the power of 1/2, or take the square root. This means the same thing. And we use a property of their exponential function to simplify this to e j pi over 4. And this converted into rectangular form is equal to cosine pi over 4, and imaginary part sine pi over 4, which is equal to square root 2 over 2, 1 plus j. That's a solution for part B. Now for part C, we can again use a property of the exponential function to rewrite this as e to the third power multiplied by e to the j4. And let's start working with e to the j4 and convert that into rectangular form. So we have cosine 4 plus j sine 4. And there's something clear I want to make here, and that we're working with 4 radians. Unless clearly specified, like this, 4 degrees, always assume that you're working in radians. That's important for your calculator. And this is equal to minus 0.654 for the real part, and the imaginary part is minus j 0.757. Now we also have e to the third power, so that is equal to 20.085. So these two are being multiplied, so let's simplify this. 20.085 multiplying the bracket of minus 0.654 minus j 0.757, and this, by expanding the bracket, is equal to minus 13.129 minus j 15.2. That's your solution for part C. So yeah, that's all I have for complex numbers in this video. I hope you enjoyed it and learned something new. And don't forget to like and subscribe, as this supports the channel. Thank you very much for watching.